Hey. So going to jump right in. Section 11.2.2, day two of probability. The first part was all talking, kind of defining what probability is and talking theoretical versus experimental. And now we're going to kind of see how we can use that in everyday situations. Our EQ is how can I find the theoretical probability of an event occurring? Again, experimental is based on results that happen. So for the most part, experimental probability is the numbers are right in front of you. So we're going to kind of focus on the theoretical side. Again, just to kind of keep the practice going of a multiple choice ACT type question in the math portion. This says when x equals 3 and y equals 5, by how much does the value of 3x squared minus 2y exceed the value of 2x squared minus 3y? So that phrase, how much does it exceed? How much does the value exceed? Exceed basically means how much more is the first value than the second value. So we'll be doing some subtracting here in a little bit. I'm going to start with 3x squared minus 2y, which plugging in my values, I have 3 times 3 squared minus 2 times y. That should be squared. Okay, so at this, you can just plug this in the calculator, and I would highly recommend if you're doing, if you're working on an ACT to not really let simple calculations bog you down. So this is 17. That pink is showing up weird on the video. I apologize. So then I'm going to do 2x squared minus 3y. That's better. 2x squared minus 3y is 2 times 3 squared minus 3 times y, which is 5. So if I type that in, 2 times 3 squared, and I'm putting both x and y in parentheses, which is just good practice anytime you're plugging a value in on a calculator. So I end up with 3. And the question is, by how much does the value of this exceed the value of that? So how much more is 17 than 3? They are 14 more. So you know 17 and 3, neither of those numbers are on the answer options, which is a common thing that an ACT question will do and make you think like, oh, am I doing something wrong? Nope, you're good. Just keep going and trust that you know what you're doing. All right, so Desiree and Jeremy are shooting free throws in the gym. Desiree has made 18 out of 43, and Jeremy has made 29 out of 67. Who has the higher probability of making their next shot? In order to figure this out, the only thing we can do is to use the experimental probabilities of each person's free throws thus far. So for Desiree, she has made, again, remember, with probability, it's between 0 and 1. The numerator is how many successful attempts, and the denominator is how many total attempts. The top number should always be smaller. If the top number is bigger than the bottom number, then you have over 100% probability, and it's not possible. So she has 18 out of 43, which as a decimal, 18 out of 43, that zero is not necessary, but is 0.418 or about 42%. And Jeremy's stats were he made 29, so he made more, but he shot 24 more free throws. 29 out of 67 is 0.432. So who has the higher probability of making their next free throw? We would have to say Jeremy does, based on the results of the experiment thus far. It's about the only thing we're going to talk about experimental probability, but that's just an example of how you would use. So if a question asks, what is the probability that Desiree's next free throw is made, you would have to say 0.418 because she's made 18 out of 43 or 41. 0.8% of her shots. So just to remember, theoretical probability is is a fraction where the top is called the event space, and that's the number of ways an event could happen. And the denominator is the number of possible outcomes, which is also referred to as a sample space. Reviewed it in 11.2.1. Just wanted to throw it out here again. So if you throw a number cube, aka a die, aka a dice, right, six-sided cube, what are the probabilities of the following? What's the probability of rolling an even number? Well, a lot of times the sample space, when you're doing theoretical probability, that denominator is usually going to be a little bit easier to calculate. In this case, we're not even really calculating anything. If you roll a die, there's six sides, there's six possibilities. So this probability is going to be something over 6. Now the question is, how many of the numbers on the die fit this event of being an even number? Well, on a die, it's 1 through 6, and so the even numbers would be 2, 4, and 6. That's 3 of them. So the probability you roll an even number is 3 out of 6, which is 1/2, or you could just call it 0.5, 50%, whatever. What's the probability you roll an odd? Again, we're working out of 6 possibilities. But the odd numbers are 1, 3, and 5 on a die. So that would be 3 out of 6. Again, 1/2 or 0.5. I'm just going to box this and kind of keep it organized. What's the probability you roll a multiple of 3? Okay, multiple of 3 meaning, right, if I'm counting by 3, 3, 6, 9, 12, so on. Again, out of 6, the multiples of 3 on a die are 3 and 6. So our event space is only 2. There's only 2 numbers on that number cube that will fit that description. So 2 out of 6 is 1/3, or as a decimal is 0.33333333. And then finally, what's the probability I roll a prime number? If you remember, a prime number means that the only factors are the number itself and 1. 1 is not a prime number because it only has one factor, which is just 1 times 1. The prime numbers are 2 is the only even prime number. 3 is prime, and so is 5. 4 is not prime because you do 4 times 1 or 2 times 2. And then 6 is either 6 and 1 or 2 and 2. So again, we have a probability that is 3 out of 6, which is 1/2 or 0.5. Okay. Now, not super exciting because all these were out of 6, and 3 of the 4 problems that we just did were multiples of, or 3 of the 4 problems we just did were 50% chance. So let's instead look at what's the probability of rolling a 5 if you roll 2 dice. Okay. So if you roll 2 dice, what's the probability that the 2 numbers add up to 5, and what's the probability that the 2 numbers add up to 8? So what we're going to do here is we're going to say, first we have to figure out the sample space. Now, since we're rolling 2 dice and each die has 6 sides, each die has 6 sides, you might think to yourself, well, it's 12. But it's actually not 12 because we learned that if I'm rolling 2 die, die number 1 has 6 outcomes, die number 2 has 6 outcomes, and the fundamental counting principle tells us we have to multiply those together. So our sample space isn't 12. Our sample space for these problems is actually going to be 36. Okay. And if you want, go ahead and list out all the possibilities. You'll find very quickly that there's more than 12 ways to roll 2 die. So both of these are going to be out of 36. Okay. So how many ways? Let's focus on rolling a 5. How many different ways can I roll a 5? Well, I could roll a 1 and then a 4. I could roll a 2 and a 3. I could roll a 3 and a 2, or I could roll a 4 then a 1. Those are the only 4 ways. So my experimental probability of rolling a 5, so the probability of rolling a 5 is 4 out of 36. Okay, there's 36 ways to roll 2 die. 4 of those ways end up in me getting a sum of 5. Well, 4 out of 36 is 1/9 because I can divide both those numbers by 4. And if you don't know this trick on the calculator, this is super helpful. You do 4 over 36, and then you just hit the math button and you hit enter twice. This will actually reduce the fraction for you. So you don't have to really worry about reducing fractions. You can just type the fraction in as you have it, hit math, enter, enter, and it'll reduce it if possible for you. If you get the same fraction again, then it just means it couldn't reduce. So 1/9, I can just type 4 over 36 and it'll give me the decimal, is 0.11. So about 11% chance if you roll 2 dice that you're going to get a 5. What about the probability that I roll an 8? Is that higher or lower? Well, let's take a look. I have, again, I know I'm working out of 36. So I can't roll a 1 because in order to get a sum of 8, the other die would need to be 7, and that's not possible. So I have a 2 with a 6. I have a 3 with a 5. I have a 4 and a 4. Now, here's what's kind of goofy is like I can do 5, 3, right? These are 2 different outcomes. 3 first, 5 second, and 5 first, 3 second are different. I can't list 4, 4 twice because these are truly identical. So 4, 4 can't be repeated. Okay. So I'm going to go ahead and move this up. And then finally, my last possibility to get an 8 would be a 6 and a 2. So there's 5 different ways that I can roll a sum of 8. So my probability is 5 out of 36. Okay. So the probability of rolling an 8, I can check here real quick. 5 out of 36. 5 is prime, so I know it can't reduce. And sure enough, the calculator tells me that. And then 5 out of 36 as a decimal. Because it's tough to compare like 1/9 to 5 over 36. Now, it's not tough to compare. If you were to look at this before I reduced and I saw 4 out of 36 and 5 out of 36, and I said which one's more likely, obviously it's 5 out of 36. But if you've already reduced the fraction to this, those numbers are a little bit tougher to compare, and that's where decimals can help us with this. So 5 out of 36 is 0.138, and then the 8s repeat. So if we roll 2 dice and add the numbers, which has a higher probability, I'm going to box this in. 8 is more likely than 5. And again, the numbers we just found are the theoretical probabilities. I don't have dice. I'm not rolling dice to do an experiment. I'm just finding the probability if I were to carry this out. So another example is, let's say you draw a marble at random from a bag, and that bag contains 14 red, 10 pink, 18 blue, and 6 gold. I grant you that this is not a super, super likely real world situation, but this is your classic probability question. There's a bag with some marbles. They have all these different colors. What's the probability that the marble you draw is not pink? Okay, I'm going to pick one marble out of the bag. What's the probability that it is not pink? So first, again, let's start with the sample space because the sample space will be the same for all of it. The sample space is just how many marbles are in that bag. So this is the first time really that we're adding. I'm going to add all those numbers up, and there are 48 marbles in the bag. So I'm going to go ahead and put over 48 because I know that there's 48 to pick from, and so each situation will be, the sample space will be 48. What's the probability that the marble is not pink? Okay. Well, if you think about which marbles are not pink, those are the red ones, not the pink ones, the blue ones, and the gold. So I could take 14 plus 18 plus 6, and that's 38. And some of you might be saying, well, couldn't I just take 48 because there's 48 marbles and subtract off the 10 pink ones? And you're absolutely correct. That's called the complement. We're not really going to get into it, but that's another way you could get the event space. So 38 out of 48. Again, if you can reduce, we want you to reduce this fraction. So 38 out of 48 is 19 out of 24. And then 19 out of 24 is 0.7916 repeating. So the probability of not pink is 19 out of 24 or 0.7916. So you have almost an 80% chance of that marble not being a pink marble. Okay, same idea here. Instead, so the marble we pick, like we're back to square one. Okay, all the marbles are in the bag. There's no like we don't have to worry about, oh well, what about the one you took out? Nope. Like reset. What's the probability that I get either a blue marble or a gold marble? Well, again, that I can just take. All right, I got 18 blue marbles and I got 6 gold. So what am I going to do with those numbers? I'm just going to add them up. 18 plus 6 is 24. Okay, so 24 out of 48 is my probability. That will reduce to 1/2, which we know is 0.5. So the probability that a single marble is blue or gold is equal to 1/2 or 0.5. Okay, and again, these are experimental probabilities. I don't have a bag of marbles to actually try this out, but these are just the experimental probabilities of these. Everyone makes mistakes, right? None of us are perfect. At this point, 2 things happen. I say experimental probability, but I actually mean theoretical. And then I skipped the another problem. So if you really care to see it, you can look at the completed notes, but that's why the video jumps. And then finally, we're going to wrap this up with a little geometry question, bring in geometry, our geometry knowledge back into probability and advanced algebra. It says a batter strike zone depends on the height and stance of the batter. What is the geometric probability that a baseball thrown at random, and this next phrase is important, within the batter strike zone will be a high inside strike? Okay. So this given information, this piece of information that we are told that it's in the strike zone, that's going to be our sample space. Okay. We know it's in the strike zone, which means we know that the ball landed, oh boy, the ball landed somewhere in the big rectangle. Okay. So if we think about sample space, basically asking how big is the strike zone? Well, the strike zone is 17 inches wide by 22 inches tall. A rectangle is simply base times height or length times width. So our sample space is 374 square inches is what the units would be. We don't need units for this because we're going to end up dividing 2 numbers. And then the question was, what's probability that it will be a high inside strike? So the high inside strike is this much, much smaller rectangle that is in the upper right-hand corner. That rectangle is only 4 by 6. 4 times 6 is 24. So that is going to be our event space. Okay. So 24 divided by 374. Again, I could reduce that fraction. Most of the time, we like to just go right to the decimal. I say most of the time. I'll contradict that statement in the next video or in the next couple of videos. 0.064, which is about a 6.4% chance that baseball is thrown in the high inside strike zone. Okay. So to summarize, how can I find the theoretical probability of an event? Again, this is a personal recommendation, but we are going to first calculate the sample space. And again, the sample space is the number of possible outcomes. And the sample space goes where? in the probability fraction. It goes on the bottom. Okay, so again, it's a personal preference. The bottom of the fraction we're going to calculate first, and then we can calculate the event space